Hello AP, this is Mrs. Sargent and this is section 13.2, the equilibrium constant. So the equilibrium constant is the law of mass action, and the equilibrium constant, which is K, notice that this is a capital K, where the rate constant was a lowercase k. Really wish they used a different letter, but they didn't, so just there's two different K's. And it can be denoted by any of the following. So Kc, which is normally looking at concentration, it can just be K, or it can be KEQ, which means equilibrium. These all refer to the same thing. They just have different ways to denote it, but they're all equal to one another. So for a reaction, this is just made up of letters Ja plus Kb yields Lc plus Md. And it's a reversible reaction as well. So the equilibrium constant can be found by taking the concentration of your products raised to the power of the coefficient. So I like to think about this as K is equal to concentration. Remember the brackets refer to concentration products raised to the power of their concentration. So products raised to the power of Y divided by the reactants raised to the power of their coefficient, which we're going to call X. And of course, if you have more than one, then you're multiplying them together, as is shown here. So remember, brackets mean concentration, moles per liter, which is also equal to the molarity. So this first example, it says write the equilibrium expression for the following reaction. We have 4 moles of ammonia gas reacting with 7 moles of oxygen, producing 4 moles of nitrogen dioxide gas and 6 moles of water vapor. So for our equilibrium expression, writing the equilibrium constant, we're going to look at the products because those are on the top. So we have the concentration of NO2 and the coefficient is 4, so raised to the power of 4, times the concentration of water raised to the power of its coefficient, which is 6, divided by our reactants now, NH3, concentration of NH3, raised to the power of 4, and then oxygen raised to the power of 7. So that is going to be our equilibrium expression. There we go. So finding the equilibrium constant. If we know the equilibrium conditions, we can calculate the equilibrium constant. Only gases and aqueous solutions are used to write the equilibrium expression. So we're only looking for things that are marked as a gas or as aqueous. So here in this example with calcium carbonate decomposing to form calcium oxide and carbon dioxide. Now you'll notice we have a solid, and a gas. The only thing from this equation that is going to be in the equilibrium expression is going to be our gas. So this is just equal to the concentration of our carbon dioxide. If an equilibrium reaction is composed of reactants and products all in the same state, then it is said to be a homogeneous system. If they're different, it is termed heterogeneous. So the value of K can be calculated easily if the original equation is manipulated as shown in the table. So this is our original reaction that we looked at in the equilibrium expression. And all you're going to do to solve for the value of K is plug in the concentrations. Now, if you notice in this next column here, the products C and D have now become the reactants. So this is the reaction has been reversed. So this is called K prime. And so you're still going to write it the same way, but if you've already calculated the equilibrium constant value for the forward reaction, you can take the inverse of K to find the value of K prime, and you will get the same answer. Now, if you have an example like this, we're back to the original reactants and products, but now we have this N out in front of our coefficient J, and so you are going to raise K to the power of the coefficient. So this would be like if the reaction is doubled, you would take whatever your value is that you calculated for K over here, and you would just square it because that would be raising it to the power of the coefficient. For a two-step reaction with K1 and K2, as the K values for each step, the K for the overall reaction is going to be K3, so we're going to take K1 and multiply it by K2, and that's going to give us the K value for the overall reaction. The units for K depend on the reaction and take into account non-ideal behavior. They will not be used. So this is one of those cases where you do not have a unit on your number. I know those are few and far between, but it is one of those cases. So let's take a look at an example with calculating the value for K. So it says the following equilibrium conditions are observed for the synthesis of ammonia from its elements. Write the balanced equation for the reaction. So synthesis forming one product, which is ammonia. Here is our balanced equation. 3 moles of hydrogen react with 1 mole of nitrogen to produce 2 moles of ammonia. So now we want to write the equilibrium expression. So K is going to be equal to the concentration of NH3, and the coefficient is 2, so we're raising that to the power of 2, divided by the concentration of hydrogen raised to its coefficient, which is 3, and then the concentration of nitrogen, and there is no coefficient, so it's 1, like so. So now we want to solve for K. In the problem, we were given the concentrations for nitrogen, hydrogen, and ammonia. So now that we have our equilibrium expression, now we're just plugging our numbers into that equilibrium expression. So the concentration of NH3 is 3.1 times 10 to the negative second, and we are squaring that, divided by hydrogen's concentration is 3.1 times 10 to the negative third, and we are cubing that, times the concentration of nitrogen, which is 8.5, times 10 to the negative first. And I was just checking to make sure that I plugged in the right numbers, the 3.1 times 10, and had the right power there. So, and then if we solve this, K is going to be equal to, if you just plug it into your calculator, 37,950. But if you notice, we have 2 sig figs in the coefficient, so we're going to round this to 38,000 for our K value. Now, if the reaction is reversed and the coefficients are doubled, so we said if we're reversing it, that would be K prime. So that's going to be 1 over K, and then we need to square it, so because we're doubling it as well. And when we do that, 1 over 38,000 squared, that is going to be equal to 6.9 times 10 to the negative 10th. So the equilibrium position is a set of equilibrium concentrations. It depends on the initial concentrations. It does, K does not depend on that. So here are the initial concentrations for experiment 1 for fluorine and hydrogen reacting to form hydrogen fluoride. We start with all reactants and no products. And the equilibrium position when the rate of change is exactly the same as there. And the K value is 0.0115. Now in our second experiment, we start with all products and no reactants. The equilibrium position is given here. And the K value is still 0.0115. And then in our third experiment, we start with only reactants, but we have twice as much hydrogen as we have fluorine. And equilibrium position is given, and still the K value is 0.0115. So your K value is always going to be the same, no matter what your values are. The initial concentrations are just going to depend on where does that graph that we looked at in our last lesson level off, so the rate of exchange is the same and we don't see any changes in concentrations. So a big thing to note is that K changes with temperature, not with concentration or pressure. So like we saw in on our last slide, these concentrations were changing and our K value was the same. Same thing if we were changing the pressure, we would not have a change in our K value. The only thing that can change it is temperature. So if you look at the gases in the flask on the left, they are equilibrium in a ratio of 8 hydrogen to 4 nitrogen and to NH3. Solving for K gives us a value. In the middle flask, nitrogen is added. When added, it increases the number of overall particles, forcing hydrogen to react with the new nitrogen and to form ammonia. After that ammonia is formed, as shown in the flask on the far right, the ammonia would be forced to decompose and reform the reactants to reestablish equilibrium. So the ratio of the products to the reactants, or your K value, your equilibrium constant, is still going to be the same. Okay, so that's it for 13.2. We will take a look at 13.3 and 13.4 in a new video. Thank you. Have a great day.